Hello students, in previous lecture we have solved density of states and it is for the three-dimensional case. So in this lecture we will see the average energy. So let's start. So in while you have calculated the density of state in three-dimensional case, so that is finally we have calculated you can say we had calculated the density of state as 2 pi v into, okay, so this was the part you have calculated and we have multiplied it by 2 because by using Pauli's exclusion principle each energy state allows 2 electrons. That's why we have multiplied by 2. So if it is the case, then the final density of state that we have obtained, it is 4 pi v into twice m upon h square raised to 3 by 2 into e raised to 1 half. So that we have calculated. So see here, if we see actually this graph, so Ze, if I plot energy on this axis, x-axis, and Ze on y-axis, I can plot the graph. So because you know y square is equal to 4ax. If it is the graph, it is open towards y-axis. So we will plot these graph in only x-axis in first quadrant. So this graph is like this. But if I actually see this graph, if I match this graph with the practical results, I can see this graph is something like this. It increases and then it decreases like this. So in order to understand that, we will actually attach the Fermi-Dirac distribution function. So we have used the Fermi distribution function, which is f of e is equal to 1 upon 1 plus exponential raised to e minus ef upon k beta t. So it has different values. F of e is equal to 1 and f of e is equal to 0 at t is equal to 0 for these two conditions. We will see this condition in detail. So first condition is this. So f of e for t is equal to 0. Okay. So original function is f of e is equal to 1 upon 1 plus exponential raised to e minus ef upon k beta t. Okay, so this is our original function. So at t is equal to 0, what will happen? At t is equal to 0, this will become something divided by 0. So something divided by 0, it will become infinity. But it will depend whether if e is greater than ef, then it will be positive. If ef is greater than e, then this will be negative. So if the numerator is let's consider first case, e is greater than ef. So then this numerator is positive. So positive thing divided by 0, that convert it into positive infinity. And exponential raised to positive infinity is infinity. So infinity plus 1, that is again infinity. 1 upon infinity is 0. So for this case, f of e will get converted to 0. And for the second case, when e is less than ef, so energy E is less than ef, in that case this numerator will be negative, and negative number divided by t is equal to 0. So negative number divided by 0, that becomes exponential raised to minus infinity, and exponential raised to minus infinity is actually 0. Okay, it is 0. So 1 upon 1 plus 0, that convert it into 0. So f of e is equal to 0. I think you must be remembering the exponential function e raised to x, which is equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus x raised to 4 upon 4 factorial, like this way up to infinity. So now we have multiplied the original function, that is 4 pi v 2m upon h square raised to 3 by 2 into e raised to 1 by 2 by the Fermi distribution function. If we multiply these, we will get some important result. So that is, so let's say I plot it here. So the function becomes like this. Okay, so it gets stopped at this Fermi, you can say Fermi energy. This is Ne. So it increases and at one point when the energy, x-axis is energy, so energy when up to Fermi energy, this energy is less than EF. When energy is less than EF, the Fermi, you can say this function is equal to 0, and energy, when energy E is greater, sorry, the this function is 1. Sorry, why I have written 0? It is 1. So when energy E is less than EF, the Fermi distribution function has value 1. So this value, okay, this value will be 1. So 1 multiplied by this, so it will remain as original function. So up to this point, EF, the original function will remain. But what happens after EF? After EF, the E is greater than EF. So in this region, so let's say this is your first region, this is your second region. So in second region, E is greater than EF. If E is greater than EF, in that case, the value of Fermi distribution function is 0. So if we multiply, so in this case, it will become 0. So if it is become 0, so whole thing, this whole thing multiply by this 0, that will become 0. So this function remains at 0 position. So this scenario, so function increases, it suddenly becomes 0 at Fermi energy and it remains 0. This scenario is for t is equal to 0. Okay, this is the first case. Now we will consider the second case for, let's say, t is slightly higher than, so let's say another temperature T2, which is slightly higher than t is equal to 0. So let's say 300 degrees Celsius. So at this point, what will happen? It will increase and it will slightly decrease, okay, at half position. So half of this height, it will be like this. So it will increase and it will start decreasing. Suppose I increase the temperature T3, which is greater than, let's say, T2. In that case, this probability density will move to the right side, okay, and the total area under curve, that will always remain constant, okay. So this curve, so first of all we have this curve at t is equal to 0. So this area under this curve, whole area, that will always remain constant. So this area plus this graph's area plus this graph's area, this area will always remain constant. So okay, so what is the meaning of this graph? We will try to see. Okay, so let's say I will draw one graph like this. So this is Ne and this is energy. Okay, so as the, you can say as the energy increases, okay, so let's say this is at temperature T is equal to 300 Kelvin. Okay, so at 300 Kelvin, what will happen? This graph will be like this. So it will never become touch this axis. So it will slightly increase. So this means, let's say at this point energy is E. So at 300 Kelvin, there are some electrons with energy. So these many electrons, this is the number of electrons per unit volume. So these many electrons are there with this energy. So electrons energy of this, we can say of this energy, there will be most of the electrons with this energy, and there will be some electrons with higher energy. And you can see, let's say this energy is Fermi energy. Let's say this energy is 100 kilo electron volt. Okay, so having a electron with energy 100 kilo electron volt, its probability is not 0 even at 300 Kelvin. Okay, so that is the important message that we have to see, that its probability of you can say its probability or its number of electrons with that high energy is less, but it is not, that probability is not 0. That means at 300 Kelvin, okay, so at 300 Kelvin, let's say, so I have a graph something like this, it will not become 0. So this is your Fermi energy. Okay, so number of electrons with higher and higher energy. Okay, so number of electrons will increase. So number of electrons with this energy will increase. It will become maximum at Fermi energy. Then it will slightly decrease, and okay, so it will it will become maximum, and it will with higher energy, you can say number of electrons will decrease. So with this, what we are going to do, what is the average energy of the electron, that we are going to calculate, because average energy is important at particular temperature. So Fermi energy is the topmost energy level at T is equal to 0, that is known to us. At T is equal to 0 Kelvin, the Fermi energy F of E is equal to 1, as E is less than EF. If it is the case, we will take the value of F of E is equal to 1 in our calculations. So our original equation was this. So in order to calculate the average energy, we have to integrate from 0 to n, means n is the total number, last energy state, and you can say here, here last n combinations, and here we are integrating it from the first zeroth energy level to the Fermi energy, that is topmost energy level at 0 Kelvin. Okay, so if we do that, we integrate it like this. So value of this part, it is equal to 1 if E is less than EF, means energy is less than Fermi energy. In that case, this part's value is equal to 1. Now the total energy, you can say n can be calculated by this formula, 0 to F Fermi energy, 4 pi V into twice m upon h square raised to 3 by 2 into e raised to 1 by 2 into 1. So its value is 1. It is taken at T is equal to 0 Kelvin. Okay, now there is only one variable, it is e raised to 1 half. We have to integrate it with respect to E. So if we integrate it, so these things, okay, these are the constants. I will take it out of the integration as it is, into e raised to 3 by 2. So integration of e raised to 1 by 2 into dE. This much simple integration will remain. So it is nothing but e raised to 1 by 2 plus 1 upon 1 by 2 plus 1. So it is e raised to 3 by 2 divided by 3 by 2. So that integration is calculated, and if we substitute the higher value of the limit, it will become EF raised to 3 by 2 upon 3 by 2. And if I put the lower limit, so if I put this lower limit as 0, the second part will become 0. That's why I have written first part, and it will finally become, so I will take this 3 by 2 with this 4, and it will become 4 pi V upon 3 into twice m upon h square raised to 3 by 2 as it is, into EF raised to 3 by 2 as it is. Now if I try to rearrange this term to calculate the Fermi energy, okay, so this is my Fermi energy. So what is that Fermi energy? So what I have done, so I have taken this part on the left hand side. So what I did, n into 3, okay, divided by 8 pi V. Okay, so 8 pi V is divided by this n, and this 3 is multiplied to this n. Okay, so I have done this, okay, into h square upon twice m raised to 3 by 2, okay, which is equal to EF raised to 3 by 2. So here what I will do, I will take the you can say ratio of these terms, means take the on both sides I will increase means I will power it by 2 by 3. If I do it, okay, so I have to take its power as 2 by 3 and its power as 2 by 3. So this 3 and this 3 will get cancelled, this 2 and this 2 will get cancelled. Similarly this 3 by 2 and 2 by 3, this will get cancelled. So this will remain, its power will remain as 2 by 3. Okay, so 3n upon 8 pi V raised to this 2 by 3 will remain, and this h square upon 2m will remain as it is. So this is the Fermi energy. This you can say this energy equation is very important. In most of the cases, if you know the number of electrons per unit volume or electron density in the particular solid, in that case Fermi energy of that solid can be calculated. Okay, now average energy. Okay, so this is the formula for the average energy. So average energy is given by 1 upon n into energy integration from 0 to EF, that is the final energy. So E is the energy into the, you can say, NEDE. So NEDE is known to us. Okay, this is known to us, and the value, this calculation is for T is equal to 0. Okay, so for T is equal to 0, for E less than EF, all energy state will be have energy less than Fermi energy. That's why we can take the value of Fermi distribution function as 1. And if we now integrate it, now this 4 pi v into twice m upon h square into raised to 3 by 2, this will remain as it is, and these two terms will get added. So e into e raised to 1 by 2, so it will become e raised to 3 by 2. This its integration is there. So this 4 pi v into 2m upon h square raised to where is that, 2m upon h square raised to 3 by 2 divided by this n will remain as it is on left hand side, and you can say we have to find this integration. So if I try to find this integration, what is this integration? E raised to 3 pi by 2 upon pi by 2. Okay, but value of n, what is the value of n? From the previous slide, value of n which we have calculated, it is 8 pi v upon 3 into twice m upon h square raised to 3 by 2 into E Fermi energy raised to 3 by 2. Okay, and if we have calculated this value, so we will substitute the value of this n. If we substitute the value of this n as this value, okay, this is the value of n in this integration, so we can see this 4 pi v upon 3, okay, and this you can say these terms, okay, so see here carefully, I will cut necessary terms. So this 2 pi upon 3 2 pi upon h square raised to 3 by 2, this term will get cancelled with this term, okay. Then 4 pi v, okay, 4 pi v upon, so 4 pi v upon 8 pi v, okay. So this 4 pi v upon 8 pi v will, okay, it will go, and I will get just 1 by 2, okay. So 4 pi v 1 is 4 pi 1 v divided 4 pi v 2 is 8 pi v, and this 3 will be as it is there divided by this 3, okay, into EF raised to this 3 by 2 is there, into this EF raised to 5 by 2 divided by this 5 by 2 will remain as it is. So which gives me 3 by 5 into EF. Check. So this 2 by 3 will be there, and this will become multiplied, so it will become 2 will get cancelled, okay. So this 2 and this 2 will get cancelled, this 5 by 3 will be there, so if this 3 goes off, it will become 3 by 5, EF raised to 3 by 2 and EF raised to 5 by 2, so 5 by 2 minus 3 by 2, that is 1 by 2, okay. So that gives me 3 by 5 into EF. So this means average energy of the electrons, it is given by 3 by 5 times Fermi energy. So this is very important equation again. So here we have calculated the average energy of the electrons. So what happens, this is Ne, okay, and this is the energy. So if I have an equation something like this, okay, so let's say this is my Fermi energy, okay. So I will have some average energy. So average energy is 3 by 5 times Fermi energy. So if the Fermi energy is the topmost field energy level at 0 Kelvin, so average energy is 3 by 5 times Fermi energy. So it is slightly lesser than the Fermi energy, that is obvious. So 3 by 5 is nothing but 5 ones are 5, 5 zeros are, so then it will become 30, so 5 6 are 0.6 times Fermi energy. So average is equal to 0.6 times Fermi energy. So that is the, you can say, final equation that we have obtained. So with this, we'll stop at this point. Thank you for watching.